Okay, they have getting this way, and this is over here, it's over there. So yesterday we discussed at length what this is all about. That what we're trying to do is add up. It's kind of like, you can think of sort of as like all the little torques that are caused, all the little resistances to rotation that are inherent in every piece of this rod everywhere. So then those things come out as little slivers. Those slivers are the like a little piece of the length, or dr. That's multiplied by the linear density, which is mass over length. And then we just take that from, if this is our focus, right, then this third and this, that's where they get those limits. And then by executing it, you get the right answer there. Questions on that part? Okay, then the other part, the thing that I wanted to make it bigger. Okay, so let's see. Get rid of that. That didn't work. Let's see. So go away. That was fun. I wonder if it's recording this. All right. So I mentioned this yesterday, and it's the center of mass, or I'm sorry, the moment of inertia of the center of mass. So I did make a mistake there. Please make sure you correct that. It's the moment of inertia at the center of mass. So it's kind of like with that bar, it's like you spin it in the middle, and then the then this extra part, this R, yesterday I denoted as D. It's still the same thing. It's the difference between the center of mass and the pivot. Okay, so let me say that again. Well, I record this, hopefully. Let me say that again. This is the moment of inertia at the center of mass. So it's, what is the moment of inertia if you were spinning that object at the center of mass? So that's why it's 1/12, because that's for a bar spinning in the middle. Then you say, what's the distance between the center of mass position and the pivot that you are being asked about? That distance is, this is R right here. That's this R. Okay, so if we take this, so this center of mass and the pivot, 1/3, 2, okay, so then, or the center of mass thing in the middle, 1/12, it's like when you derive that one. The same way we did the other one. Okay. It's right here. R, right. It's R is the distance from the center of mass to the pivot. And you just take the mass like usual. So if we look over here, see, it's the same mass. And then what is that distance from there to there? Well, that's just algebra, right? Because what's half? Like, this is 1/3. And then the distance from here to here is 1/2 minus 1/3. And what's 1/2 minus 1/3? Oops, jeez. Right, and so then there's 1/2 is 3/6 minus 1/3, which is 2/6, so you get 1/6. That's where they get this. Questions on that? So again, to walk through it clearly, you use the parallel axis theorem. You have to have the center of mass at the pivot. I'm sorry, center of mass at this, the moment of inertia at the center of mass. Then you put that in your equation, use the distance between the center of mass and the pivot, and then you get your answer. Frankly, this only really helps you if you've memorized the moments of inertia. If you have them memorized, then it's helpful. If you don't have them memorized, it's not helpful, because you're going to derive it anyways. So what's the point? Okay? I wish it would recognize its own. Then on second part, you know what I should do? I should do this. As the rod is released from rest from a horizontal position as shown above, calculate the linear speed of the bottom end of the rod when the rod passes through the vertical. So when it swings down from here to here, what is the tangential speed of the bottom of the rod? So then we did a problem kind of like this, right? And here, points, we can see the points. So we have 2 points, okay, and we're saying this potential energy is going to equal the angular kinetic energy as it swings down. Does that make sense to you? Yeah, the potential energy that it has. Now, let's think about that for a second. Oh, shoot, am I recording? Yes. The potential energy that it has, potential energy of gravity is what? It's the energy essentially of falling. So what can fall? When you have an object, what we're always concerned with is the center of mass. So how far can the center of mass fall? Well, we already know from our discussion of the last part A that the center of mass is 1/6 L from the pivot. Everybody okay with that? Okay. So then the center of mass can only drop 1/6 L. Right? Everybody does that make sense? Because this can only fall down to there. Here is the mass is here. And that distance right there is L over 6. Yeah, it wouldn't rotate. It would just sit there. But I mean, it's a good question. We can get to deal with these things. Questions? Any other questions? Okay. Where did the top go? That's where they get the derivation equation, and then they're just doing a bunch of conversions. Because what is I? Well, you just calculated that in part A. I was ml squared over 9. Omega squared becomes v over r squared, and solve through and get your answer of v is 2 squared of gl over 3. So that's just a bunch of algebra.